This is the third of 6 videos on spectroscopy for organic chemistry. In the first one, we again looked at the NMR, how it works. In the second one, we started discussing how to go from structure to spectra. And all we did is look at the number of non-equivalent protons you can determine for its structure. And then we did look at how to position those along a 0 to 10 ppm, baseline, and where to put those. So let's move beyond that and look at integration. So let's review our steps. If we have a structure for which we have to determine spectra, the first step is to determine number of signals expected. How do we do that? Look for number of non-equivalent protons. And we said those are equal if we can discern all signals, but at least this signal number of signals cannot be higher than the number of non-equivalent protons. Non-equivalent, just abbreviated there, non-equivalent protons. So that's what our first video started off, our second video on structure to spectra analysis. We looked at that, but then we finished with arrange those signals. And we looked at 5 categories. We said we have alkyl, allylic, heteroatom affected, vinylic, and aryl. So we arrange those signals that we get. We can arrange those signals on the spectra from most shielded to least. So we'll going from left to right. Most shielded to least. The upfield side, we said, and the downfield side. So let's move to our third step in this process of going from structure to spectra. Number of the signals, arrange the signals, and then use ratio of differing protons in the structure to set, I should say, peak area, not size. But here the peaks we're saying are so thin, or narrow in their distribution, that we're going to just look at the size of these two signals. So let's take our ester here. We have 3 methyl groups that are off of this carbon that's connected to what's called a carbonyl, and we have this methoxy group. So we know this, that because there's bond rotation, these 3 methyl groups are equivalent. It may not look like that in this drawing. This one's up, this one's down, this one's straight out. But if we were to put this into a model, we know that we could rotate this very quickly, and we would not be able to know, after having picked any one of these 9 protons, where to find that one again. So these 9 protons, 3 here, 3 here, and 3 here, would be equivalent. And now let's just review, the steps. These 3 would be equivalent to these 3, which are equivalent to these 3, but are not, of course, equivalent to these 3 on the methyl group over here, because this is connected to an oxygen. So we would have 2 signals, and that's what we're showing here. But how would we arrange those signals? Well, remember, we have to look at those 5 regions. What type of proton do we have? Now, we can take a representative of any one of these 9. So this methyl group, I could say I'll take one of those. Well, that one is off a sp3 carbon, which is off an sp3 carbon. So these that are called A protons, these that are the A-type protons would be all alkyl protons. What about this one? Are these 3? We can take any one of the 3 as a representative and say it's bonded to an sp3 carbon that's bonded to an oxygen. Oh, these are heteroatom affected. So this would be downfield from 4.5 to 2.5. So we see B, and we could, again, if we're proposing spectra, we could say I'm going to expect to find it somewhere in that range from 2.5 to 4.5. Now let's move into that third step. So the number of signals we'd expect to have 2. We put this one upfield and this one downfield based on our understanding of the 5 areas where the protons can fall. So what do we do now, though, in terms of peak area? Well, how many protons do we have that are alkyl? Well, we have 9. And here, heteroatom affected, we have 3. So we would know that this peak for A would be 3 times, in terms of peak area, the area for, I guess, the heteroatom affected protons, B. So we'd expect this area to be 3 times the area for this peak here. So what we can do by setting up integration numbers, we can just say we could have a program that could calculate, if we were looking at spectra, could calculate the area under the curve, and we could just have a unitless number and say it's 3.01, and it's not going to be perfect, and this would be 1.15 if we were going spectra back to structure. We could say that's roughly a 3-to-1 ratio. But of course, we're proposing spectra, so we can be as precise as we want to be. We can say an integration value of 3-to-1, where the smallest peak is just given a unitless value of 1. But relative to that 1, this is 3 times the area. So we can write 1 to 3. These are integration values above the signals. Now, please note, we did not say, or I'm not saying that there's only 1 hydrogen for this signal at B, and there's only 3 hydrogens for this signal for type A protons. We know it's just a ratio. So it's actually 3-to-9 if we look at the structure. But we don't put 3-to-9. We put the ratio in the lowest, I guess, factor or lowest number. All right, that's integration. Let's move into splitting, and we'll be done with the 3 boxes we have to unpack in our sort of 4 steps. Number of signals, arrange the signals, look at integration, and look at splitting. So what is splitting in the proton NMR spectroscopy? Why do we have it? Let's take, I guess, a signal for the yellow shaded proton. So let's say this is the one that's generating a signal. And of course, we've looked at integration of the signal and such. And what we can do is look at the splitting, the fine splitting of that signal, these details of that signal. Is it a doublet? Is it a triplet? Is it a quartet? What we mean by that is, does it look like this? That would be a triplet. Does it look like this? The signal, that's a doublet. How do we explain these types of splitting patterns? We have to look at the neighbor, not the one that generates the signal. That would be the one in yellow. But the neighbor, we're going to indicate that by this one in red here. We're saying this is a neighboring proton that has a whole different signal, but he's next to the one that's generating a particular signal. He's on an adjoining carbon, a vicinal carbon next door. The big field, of course, has aligned both, or has caused this one to be opposed and this one to be opposed. But we're looking at taking the one that we're looking at, that's a line, is going to flip to a opposed state. What could the other neighbors be set to as far as their magnetic field? Well, they could be aligned or they could be opposed. And that's what we're going to look at as far as our choices for the neighboring protons. So those in red that are nearby the one in yellow here that gives our signal can affect the overall field that this one in yellow feels. Because if it's aligned with the big field, then this precesses a little faster. If this is opposed to the big field, this neighbor, then it precesses a little slower. So let's take that one and define it in an actual structure. So let's say we have ethyl bromide. So we could take ethyl bromide, and we know, just kind of running through the steps, that these 3 protons would be non-equivalent to these 2. These would be these would be truly equivalent. These would be enantiotopic, because if we take one of these 2 and replace it with something altogether different, it would be a chirality center. But in a achiral solvent for analysis, deuterated solvent, these are equivalents. So these are equivalent to each other, but they're not equivalent to these 3. So we'd expect 2 signals, integration of 2 to 3, or so we can have that, or like I said, 1 to 1.5. So we can have that integration set, but now let's consider the splitting for this proton. That's a representative. We only have to take a representative of these two. So we can just take any one of these three. So I'm just circling this one in yellow and looking at what his splitting would be. His splitting, where do we go? To his neighbor's place, his neighbor's home. So we take a walk. This is a geminal. These would be the same, of course, so we don't. These aren't neighbors. These are the equivalent to this one in yellow. So we have to take a walk to a vicinal position, and these hydrogens are non-equivalent to this one in yellow. We only see splitting of a particular signal by non-equivalent protons. So these are not highlighted in red. So we take that walk and we say, hey, we have two neighbors. They can both be aligned with the big field as I'm precessing, or in two different ways they can cancel each other out, or they can both be opposed. That's why we get, for this particular situation, a triplet, because we can have different states for our neighbors, both aligned with the big field, precessing a little bit faster and therefore downfield, both opposed to the big field, precessing a little slower and therefore a little upfield. Of course, canceling each other out, we have two different ways to populate that sort of state. So this is going to be in area, it's going to be a 1-2-1 relationship as far as the area. So it's not level across. That one in the middle, this is a triplet, would be twice as high as either one on the left or the right. So that's how we can explain splitting. Is it's not the proton of interest, or that's creating the signal that we look at. We go to the neighboring protons to set what the splitting for this one in yellow looks like. We typically only go to vicinal relationships, that is 3 steps, 1, 2, 3. These protons off of adjoining carbons or vicinal carbons next to each other. We typically don't see geminal coupling unless we have a chirality center. Alright, so that's the basics for splitting. Let's go to a table that sort of summarizes the different types of numbers of neighbors. If we have no neighbors, then we of course have no splitting. We'd see just a singlet, a nice sharp signal. If we have one neighbor, then we of course have a doublet. We just talked about the triplet. We can have a quartet, and on down the line we can have a quintet and a septet. You can have these relationships between this fine detail of the signal that we call the splitting and the number of non-equivalent protons to the one that's generating the signal. Now when it says number of equivalent adjacent protons, we mean equivalent to each other. If you have a proton of interest, let's say here in yellow, it has a neighbor in blue, and then if there was another neighbor here that's different in green, that's going to give us complex splitting. This is just simple splitting patterns. The easiest way to say it is that you're the Joneses and you have Smiths living on both sides of your house. It's not we cannot use this table if we have complex splitting. That is, I'm the Jones and I have a Smith and Johnson both living next to me that affect me. That would be a form of that would generate complex splitting if you have two neighbors that are non-equivalent to each other and non-equivalent to you. So this is the splitting pattern. If we have neighbors that are equivalent to each other but not equivalent to us, we can use this table. Remember, chemically equivalent protons do not split each other. The signal of a proton that has n neighboring protons equivalent to each other gives us n+1 peaks. So one neighbor, doublet, 2, triplet, 3, quartet, 4, quintet, and so on. So let's look at this ether, methylphenyl ether here that has some chlorines here on the benzene ring. We look at the number of signals, we would see 3. These two protons are non-equivalent to each other based on their proximity to the chlorines and to the oxygen. They can be discerned from each other. So they would be aryl protons, of course. This would be a heteroatom affected. So we'd have 3 signals. We'd expect, let's go guess just briefly into where they would fall. These we'd expect in the 2.5 to 4.5 range. And we'd expect these in the 8.5 to 6.5 range. But I want you to notice here, focusing in just on the aryl protons, is the splitting pattern. Let's take the one in blue and say, what does your splitting look like? We don't look at him, we look at the neighbor. So we go to the carbon and take a trip, 1, 2, 3. Well, there's no proton here, so no splitting from the bottom left, but 1, 2, 3. We have a proton that's different from this one, but there's only one. So we'd expect a doublet for the signal generated by this proton in blue, and we see that. But splitting's like handshakes. You can't have handshakes with yourself, so you're going to see splitting for two different signals. Not only for this one, but if this can split this one's signal, it's the same way can do the other way around. We can have then this signal split by the proton here. The signal for the yellow proton is going to be also split then. And it'll also be a doublet because he's not close enough to these three. It's 1, 2, 3, 1, 2, 3. There's not a proton here. These do not split each other. So we'd have a doublet and a doublet. Notice they kind of lean towards each other. It's not a perfect doublet where these two are equal in height. When you see this sort of leaning, it means those two protons are splitting each other. They lean more towards each other or have a greater angle the closer the signals get to each other. But these two leaning towards each other mean that those two signals have protons that are next to each other. So that's a little trick you can use when you're going from spectra back to structure. All right, let's put all this together, this, I guess, understanding now of the three things: the position of signals, arranging those signals, integration, and splitting, by this, and using our 4 steps. So let's take diethyl ether one more time and finish the story for diethyl ether. So our first step was to determine number of signals. How did we do that? We looked at the number of non-equivalent protons. So for diethyl ether, we said that was 2. There were this type here, and we have B and A. There were 6 protons here, 4 protons here. These were alkyl because they are off of sp3 carbon. It's bonded to sp3 carbon. These would be protons that are heteroatom affected. They're on a sp3 carbon bonded to an oxygen, so I'll just put hetero atom affected, and we had our particular, we're getting ready then to bring them down. Heteroatom affected was 2.5 or 4.5 to 2.5 alkyl. So this is just the way you can kind of work through the problem. Alkyls were 0.5 or 1.5 to 0.5 parts per million. So we're going to arrange, so we're kind of jumping into arranging the signals based on where we know they would fall, or where in general they would fall. Be very careful. These are just ranges that they typically fall in. The third step was, I guess, the integration. Determine the peak and integration by looking at the, I guess, the area, ratio of areas. My pen's going out here. So we would have a 4 to 6, well that's a 2 to 3, or 1 to 1.5, and we can put that, we'll put that in on top of the signals. And then we had the splitting. So let's go ahead and set that for these two signals, and then we'll draw our spectra. Consider splitting. This produces the pattern seen within the signal, the fine detail of the signal. So what we do for splitting is, again, take a representative for protons B, any one of these 4. So grab one. So I grabbed this one, I could have grabbed this one, I could have grabbed this one, I could have grabbed this one. It doesn't matter. Once you figure out which ones are equivalent to each other, they are equivalent. So what's true for one is true for any other. So I can grab one of these B protons that are heteroatom affected. and what's true for one is true for all others. And we take a walk. Now I don't consider the splitting of this one because these are equivalent. So I have to go to a non-equivalent proton. Well, of course there's not one here. These are equivalent. So 1, 2, 3. This is not a proton, but 1, 2, 3. These carbons adjoin to each other. This one's the proton I'm looking at. This is one that's different. Now how many are different at that position? 1, 2, 3. So off of an adjoining carbon to the one I'm focusing in on. This is my sample of B, my representative. Whatever's true for this one's true for all. He has 3 non-equivalent neighbors. So I'd expect a quartet for this proton, its signal. Now for A, we can do the same thing. Take a representative of any one of the 6. So I can take this one. I take a walk. 1, 2, 3. And it has 2 neighbors. So I'd expect a triplet. Now you'll sometimes see just a noting of its splitting in text by having a Q or a T along the text describing protons within a structure. Now let's go ahead, and I kind of limited my space here to draw a spectra. So let's take this information that we now have for the structure and put it into the spectra. And you say, well, where exactly do I put it? Well, typically these pendant methyl groups would sit below 1, but we have a heteroatom that's present. So if they're a pendant methyl group, they tend to sit as a signal below 1. But with that oxygen, maybe just to get it in the right range, we're not going to be, unless we saw the actual spectra, we're not going to be 100% sure. But I'm just going to have fun. I'm going to draw a triplet in here. A triplet representing A protons. Now I'm going to come back to integration and put the integration value there. For this one, we expect it from 4.5 to 2.5, so I'm just going to put it in there somewhere, a quartet. I'm expecting to see a quartet. And now the integration, I would expect, again, to have a lower signal here, smaller signal, because there are only 4 of this type of proton, and there are 6 of this type. So we'll say 1 to 1.5. Sorry, I guess, 1 to 1.5, that'd be a 2 to 3, and it's really 4 to 6. So we don't write it as 4 and 6, we write the ratio of the areas, representing the ratio of the protons. 1 to 1.5, that's representative of 2 to 3, 4 to 6. And that's it. That's how we can go from structure to spectra problems. Bye-bye.